Okay, so let's start from the info small. So in the coming week, next week, we are going to have a long vacation. So that means we are going to miss another 2 hours again. Too bad. So I made a change to the midterm exam. So I think it's better to replace the midterm exam by a term project. Okay? So that we can use the midterm exam to do some lectures. I think that makes us better. And also, that will inspire you to learn something much more interesting. Okay? So maybe it's better to show you this. Sorry. I have prepared some topics for you. So you even one of the topics is the automatic detection of underwater propeller signals using cyclostationarity analysis. Okay. We don't know that yet, right? But that's fine. We can read it. So I want you to either use the topic that I gave you, or you can find a topic by yourself. You can pick a topic by yourself. Okay? And I think it's better to team up with your classmate. Each team has can be composed of 2 members. Each team has 2 members. So you and your team member can work together. All right? So each team has 2 members. One more time. You can find your team member by yourself. Okay? Up to you to choose your team member. All right? And then either you can use the topic that I gave you. This one, I will upload this to the iClass platform. Or this one. These are the most very interesting. The closed form estimation. The closed form estimation for frequency estimation of complex sinusoidal signals in multiplicative and additive noise. And there are lots of interesting things in this. If you read the okay, that's another topic. And also another one, this one, this is also very interesting. This is very useful for aerospace engineering students. Of a method for finding position and orientation of accelerometers from their signals. Okay? Again, I will upload this paper to your iClass platform. So you can choose the topic from the one that I gave you, or you can find the topic by yourself. But if you decide to choose your own topic, please discuss your topic with me first. Okay? So let me make sure that that topic is proper for you. Okay? So this is another topic. And also, this one. missing value recovery will encode the signals using improved low-rate approximation. This is also a very interesting topic. Now, what I'm trying to ask you is to recover the results given by the paper. Okay? You don't have to create anything new because I think you have only maybe less than 10 weeks. So the time of period is very short. The only thing you have to do is to recover all the results given by the paper. That's it. Okay? Duplicate all the results and go through the procedures. You will find there are many interesting things in the signal process, in the signal processing. For example, suppose we have some missing point. What are they? How do we recover the signals? Something like that. Okay, for this topic. And also this one, finding position and orientation of accelerometers from their signals. Some of you maybe are working in the UAV lab. This will be very useful for those who in the UAV lab. Okay? So this is also a very interesting topic. And also another one. This one. The closed form estimator for frequency estimation of complex signals. Complex sinusoidal signals in multiplicative. This is the keyword, multiplicative and additive noise. Okay? Suppose your signals are contaminated by this noise. How do we estimate the frequency of the signals? Things like this. They are very useful, very interesting. Okay? Okay. So again, let me say that one more time. So there will be no written test for the midterm exam. It will be replaced by term project. However, I still will ask you to give me a preliminary report for the term project after the midterm exam. We will find a time. We will find another time later. Okay? And then in the end of the semester, we will have you report the entire term project. Got it? So there will be no written test. No written test. Okay? So instead, the written test are replaced by term project. For a term project, you have to duplicate. You only have to duplicate the results given by the papers. Okay? And you have to hand in the paper report, the paper, okay? And also your slide, PowerPoint, but I don't like PowerPoint. I prefer to use the Beamer. Okay, I will tell you that later. Okay, got it? All right. Okay, so any questions regarding the term project? Question? Okay. All right, let's resume the lecture one more time. Okay, so let's start from defining a very interesting function. It's called impulse function. And first, let's define a delta sub delta t. It is equal to 1 over delta when the t between negative 1/2 delta and the positive 1/2 delta. And the function value is equal to 1 over delta. Okay, so this is the delta sub delta. Now, what is the area? What is the area of this rectangular area? The area of this yellow strip is equal to what? You don't know. Come on, how to compute the area of this rectangular area? This yellow rectangular area. Rectangular strip. What is the area? 1. Good. Great. Okay? The height is 1 over delta. The width is delta. So it's equal to 1 over delta times delta, right? So it is equal to 1. No matter what the delta is, this also equals to 1. Okay? Now, what if I define the impulse function delta of t as the limit? The delta approaches 0. So in this case, the function value since that delta approaches 0, right? The width of the strip approaches 0, so it becomes very, very narrow, but the height becomes very, very big. Okay? And then we define this as a delta of t. Sometimes we call this the direction. Okay, but for this case, for this definition, let me ask you. Imagine that there is a very narrow, super narrow strip. What is the area of the strip? What is the area of the strip? Again. Yes, good. It is also equals to 1 because I have told you this is true for any delta, no matter how small it is. No matter how small it is. So even for this very narrow, very, very narrow function, okay, the area under the function is 1. Okay? Similarly for this one. It is 1. That's a very important problem. Now, some other books, or sometimes you may see a slightly different definition for this delta sub delta. Okay, so maybe use this space here. Some other definition slightly different, but actually they are the same. Sorry, can you change the sign here? You may see this thing. The function value, the same, but the position is slightly different. zero in the middle. Okay, but once you take the limit, this strip also approaches, becomes a very, very narrow impulse, let me call it impulse, that T equals zero. Okay? So this definition actually is the same as this one. When the T approaches zero. Okay? And then what about now if I shift, and then define it over here. If I shift the argument, then this impulse appears over here. At T equals tau, we have an impulse. Okay? All right, a very important property is, any question? Come on, before we move on to the next one. Next one. Okay, a very important property is, if I have a function, let me for example P, and then times the delta, P minus tau, d tau. That's a very important property, okay? I claim that this equals to f of tau. Okay, so let's prove it. Okay, the way that I'm going to prove is a little bit rough. Okay, but I want you to get the idea. So let me assume I have a function f of t first. Okay, an arbitrary function. And this is tau. So this is f of tau. Now, the way I prove this is I'm going to use this Taylor's function. So again, repeat that function over here. Okay, so now we have a shifted impulse function. So let me duplicate it over here. Okay. So this is tau minus 1/2 delta. And this is plus 1/2 delta. And the height is 1/5. Okay, so the integral remember that what is the definition, critical definition of this integral? That is the area under the function. f of t times delta of t minus tau, right? Okay. So what is the area, or what is the height? That's equal to the height. Okay, let me use this. Sorry. Look at this figure here one more time. We are going to consider the area under the function f of t times the delta function. Okay, this is f of tau. That t was tau. And all the other function values are zeros for the delta function. So this is equal to f of tau times 1 over delta times 1 over delta times which is 2. Okay. Delta, maybe. And let's take the name. This is better notation. So let's see. And this is the function value of this function, the product of the f of t and delta of t minus tau, then times the width. Okay, this is the width. That's equal to tau. And obviously this is equal to 1. I'm sorry, no. This is equal to 1 and times f of tau. Okay, now this is a very important property and we are going to use this later. All right, another similar one, but slightly different. And then maybe give you a figure first. And then, okay, for simplicity, I'm going to assume my x of t defined from t equals 0. Okay, just for simplicity. And then I'm going to divide the x of t into many small strips. Now each strip has the width delta. Okay? So staircase，披萨闪电的窗。黑色标好，黑色标好。Okay. Let us see what is the limit. Well, what is the x of t? I divide it into many small streets. So this is x of 0, and this is x of q, and this is x of 2q. This delta times the delta function at 0, and then times the delta. And then use the sub delta, okay, this one. And plus x of delta times delta. T minus 4. Okay, and then I'm going to take the limit. And it turns out that this can be replaced by an interval. X of tau, t minus tau, e tau. Okay, the key point is this we divide this function x of t into many small streets, the regular streets like this. Okay, for example, the second one. Okay, let me divide it into this one. Okay? There are many streets like this. So the first function can be replaced by x of 0 times delta sub delta, or t, and then times the width. Okay, so this is another way we can represent a function. We'll see that later again when we consider it linear causal system. Okay, in that section, this becomes very obvious. So maybe you are not so familiar with this for the moment. That's fine. Just want to let you know that we have this kind of result at the very beginning. Okay, any question again? All right? Okay, before we move to the next chapter, let me show you a very interesting Now, to define a delta function or direct delta function, there are many ways, there are many definitions to define a delta function or impulse function. Another function very similar to what we just did here is the Gaussian distribution function. You can see that when the width gets narrow, the height gets bigger and bigger. Okay? But no matter how narrow the width is, the area under the function is always 1, which is similar to what I just gave you here. I'll erase this one. Okay? So this is another type of the impulse function. Yes. Here we go. This is one of the show. Okay, the Gaussian distribution. Another one is use a function. It's called Lorentz Cauchy function. Use this function to define the delta function. Okay? The shape is very similar. So there are many different ways to define an impulse function. And also this function, single functions. Okay? Alright? Okay, if you have no question, then let's move to the next chapter. In the first chapter, we consider signals. Now we are going to consider systems, continuous time systems. Okay? Alright, so what is a system indeed? Okay, this is the very rough definition. A system is a mathematical transformation of input signals into output signals. Okay, so suppose you have an input signals and you go through a system and you have the output. So the output, while T usually can be written as S represented as a function. It can be a static function, it can be a dynamic function, it can be a partial differential equation, it can be ordinary differential equation. Okay, it can be something else we define. So after you go through the system, you have the output y of t. Now in this chapter, we focus on continuous time systems. Okay, for the continuous time system, there are some properties we have to consider. We are going to consider linearity, time invariant system, or time invariant or time varying system, causality, and the stability. So these are some important properties that we have to consider for a system. Okay? Linearity. relationship. It's nothing to do with the time. For example, the spring force and y equals ant. So suppose you have spring. Okay, the spring house is K, and then you have the fibers. F. Then use y base of it. Okay, this y actually is the applied force. Okay, so y is equal to K times the delta F. Let's define the delta F is the elevation. Okay, so which means now we can use the real parameter to represent this simple system. So I have x, that's the elevation, and then I can build up the output one, which is the applied force. Applied force. Okay? So that's a very simple steady system. Or V equals IR. Right? Suppose I have a resistor. The voltage drop is V, the current is go through the resistors is I. So I is the resistance. And so I is the resistance. So I is the resistance. I is the current. And V is the voltage drop. Across the resistor. Okay. So now we have, if I have the current, then I can figure out the voltage drop. Right? So this is another simple steady system. What about dynamic system? Dynamic. Sorry. All right, now let's consider a very simple dynamic system. Suppose I have a block. The mass is M. And I know the displacement of the block is X. Right? And let's assume I have a applied force. M. Applied on the block. So we can write down the equation of motion, right? Would you write the equation of motion for me? Equation of motion using the Newton's law. Newton's law, you have heard that before, right? In either high school or another course, dynamics. Would you write down the equation of motion? Motion. Yeah? By using the Newton's law. slope, right? So what is A? Acceleration. What is the acceleration now? What is the acceleration? Suppose I have known the displacement. What is that? We have the displacement now, okay? Let's assume we have the displacement for the block. X is the displacement of the block. Okay? So what is the acceleration? If I have the displacement, then how do I determine the acceleration? We all have taken a course dynamics, right? Okay? So you should be able to give me the acceleration. If you have the displacement, then what is the acceleration of the displacement? Come on, don't do that. Do not stereotypes, okay? Give me something much more educated expression. 有小问题的 okay? What is the acceleration? Come on. We are given the displacement. Now suppose this is the x, this is the displacement. Okay? We're going to that here. X, that's the displacement. So what is the acceleration of n? Sorry? Oh. Yeah. Displacement of n. Okay? So what is the acceleration? Would you give your hand, give your hand to your friend. Give your friend a hand, give him a help. What do you mean? You don't know? Yeah. There's space in your ear. Come on, go do that. And don't do it, I don't know. You should be able to write on that. The version of second. Sorry? I don't mind that. It doesn't matter. What is that? What is that? What? Be specific. You have taken a course, dynamics, you should be able to tell me. Okay? So what is the fine, I'll talk about it and go down. Come on, anyone, give your friend help. Give him a hand. You have taken a course, dynamics, right? Okay, good. So what is the acceleration? If you know the displacement, yeah, good. Help me with that, please. Yeah, okay. We all know the Newton's law, right? Is there anyone has a problem with Newton's law? No? Have you taken a course, dynamics? Yes, you did. You have. Okay. So everybody sitting in this room have taken a course, dynamics. So you should be able to answer my question very easily. So what is the acceleration of the mass m? We already need displacement. Okay, suppose it is given. And also actually in a bell. Given the displacement already, okay? What is the acceleration? With the knowledge, with the given knowledge of the displacement, with the given information of the displacement, x of t, then what is the acceleration? Zip. 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 No. You are supposed to know that, okay? You can discuss with the classmate, your friend, okay? No problem. You are a little bit closer now, but you have to know what you're doing, okay? Don't just randomly guess. They are in trouble actually. Okay? So would you give them a hand? Give them a hand. So give them a hand. Okay? So you have the displacement. What is the acceleration? You all have taken a course, dynamics. This should be very easy for all of you. What is that? What is this? Could you explain this to the class? I mean definition. V-E-L-O-C-I-T-Y. Come on. Gentlemen. V-E-L-O, velocity. V-E-L-O, not L-A. No, acceleration. Spelling is incorrect. A-C-C-E-L-E-R. No, L-E-R. L-E-R, A-T-I-O-N. seems that you never open your textbook. Good. What is X dot? What is X dot? X dot. Mathematical definition for X dot. Okay, you have the X dot, but what is the definition for X dot? Mathematical definition. X dot is mathematical definition. Okay. And you tell me, no, what are you doing? No, what is that? I cannot read it. What's that? What is X dot? What is X dot? Your turn, eventually, Superman, Superwoman, come on. Good job. Thank you. You were written, all of you. Thank you. Thank you. Thank you. Okay, you all have learned this from the other courses. Not good. Not good. Okay? You should be able to give me this right away. Am I right? Okay? Shouldn't be a problem to any one of you sitting in this room. Okay? So you have to make sure you know why and how and the very basic definitions. Okay, that's what I'm trying to tell you. Alright? Okay, so let me start over again. So let's implement the Newton's law. So mass times the acceleration. Now the acceleration is the second order derivative of the displacement. Okay? Now later on we are going to learn Laplace transform. So if I take the Laplace transform, later on we are going to have n times s squared times the Laplace transform of x of t, and then equals to f of s. Okay? Where the x of s, we define it as the Laplace transform of x of t. And then the f of s is the Laplace transform of the f of. Yeah, this can be a function of time. Doesn't matter. Okay? So now divide through. Or maybe, let me write this, sorry. Okay, so yeah. In this case, we have an input. Here this time the input is ms squared in the denominator, 1 over ms squared. Will give us the output displacement in the S domain. So this time, this system S, it is in S domain. We have the input signal, but it is in S domain. Okay, we will see that later on in the S domain. Okay? And then the output is the displacement of the mesh, but it is also in S domain. So using this notation, we have the system 1 over ms squared. Okay, so this 1 over ms squared is used to describe this dynamic system, very simple dynamic system. Okay? Alright? So dynamic system usually involves differential equation. Okay? Or even partial differential equation. If we have a say temperature heat transfer problem or the stress problem, okay, or structure problem, then we have a partial differential equation or heat transfer problem. Alright? Okay, so now let's focus on the properties. First one is linearity. S is linear. If an only S of alpha times S plus beta times 1 equals alpha times S of S plus beta times S of 1. Okay. Where the X and Y are the input signals. And then alpha and beta, arbitrary constants. Now this is a definition. So if I have a signal X, the output is S of X. If I have a signal Y, the output is S of Y. If the system S is linear, if and only if S of alpha X plus beta times Y. So let's use the linear combination of the signal. Alpha X plus beta Y. So this is a linear combination of the signal. Then the output is simply the linear combination of the output S of X and S of Y. If this is true, then S is a linear function. Okay, let me give you one quick example. All right, for simplicity, we consider a static system. Okay, a spring constant or resistance equation, resistance. So where A is a given constant. And X can be any real number. Okay. This is is the example that I gave this afternoon in another course. Right? Okay, so this is a very simple system. So let's see. The input is x, then the output is a times x. Okay, so let's try. Let me call this left-hand side. S of alpha x plus beta y is the left-hand side. And these are the right-hand side. Okay? So the left-hand side, that's S of alpha x plus beta y. And we replace x by alpha x plus beta y. A times alpha x plus beta. Okay? So that's equal to alpha times a times x plus beta times a times y. Then what about the right hand side? Alpha times s of x plus beta times s of y. So that's equal to s alpha times s of x, that's a times x. And then beta times s of y is a times y. So now let's compare the left-hand side with the right-hand side. So obviously we have left-hand side always equal to right-hand side. So this equality holds for any xy, okay, and any alpha and beta. This can be even a complex number. So which means f of x or s of x, usually. S of x is the What about if it is not linear? What kind of situation this can happen? So let me show you another example. So this time is defined. S of x is x squared. Okay? Let's assume x is a real number. X is a real number. Then is this a linear function or not? Is this a linear system or not? Okay, so we have a then the opposite is squared. Okay, so let's find the left-hand side. Left-hand side is alpha x plus beta y. So that's equal to alpha times x plus beta times y, quantity squared. So you replace x by alpha x plus beta y, right? Okay, so that's equal to alpha squared, x squared, beta squared, times y squared. 2 times alpha times beta times x times y. Okay? What about the right hand side? That's equal to alpha times So now let's compare the left-hand side with the right-hand side. You can see that they are quite different. Okay? So the left-hand side and the right-hand side, they are not the same in general. In general means there may be some special cases. This equality, the left-hand side and the right-hand side, this equality will hold. Okay? For some special cases, the left-hand side may be equals to the right-hand side, but that is only for some special cases. But for the other alpha, beta, and the x and y, this equality does not hold. Okay? So which means this given function is not linear. And actually we call this nonlinear. Okay? So that's a very simple case. Question? And variance. Okay, let's see another problem. How many variance? next property is also very important. Okay, if I have the function S, system S, if I have a system S, now if I claim that the system is time invariant, what do I mean by that? That means if you have a signal, let me call it x of t, okay, this is the input signal. And we have the output signal y of t. Now, if you shift the input signal a little bit, say, delay the input signal half second, then the output signal also will delay half second. And the output signal, actually the shape, the output signal are the same as the y of t, except that there is a time shift. Okay, for this case it's delay. Okay, if this is true, the system is time invariant. The system is time invariant. Now, in the world of nature, you may think that this is true for every system. But think about that one more time. You have to be careful. Sometimes it may not be true. For example, let's consider when you take a bus to school. Okay? Suppose you left your home at say 8 p.m. Okay? And then you jump to a bus at 8:30. You jump to a bus at 8:30. Okay? And then you get off the bus at, say, I don't know, maybe 9 o'clock. Then you are safe to enter my course at 10 o'clock, for example. So 10 or 9:10, sorry. 9:10. Okay? So you jump to a bus. Get off the bus. Okay? And then you enter my class. Right? Okay, and then what will happen? One day, for some reason, you left home a little bit late, so you did not catch the bus at 8:30. So you are going to miss this 8:30 bus. So probably you are going to get on the bus at 8:45, for example. Okay, for example, just for example. You get on the bus. And this time, you are going to get off the bus. And now, even though there's a 15-second delay, right? From here to here. From here to 8:45, from 8:30 to 8:45. There's a 15 seconds delay. But because you are taking a bus, so sometimes due to the traffic jam, your bus takes a little bit longer than before. Okay? So maybe you get off the bus at 9:15. And then I already locked the door, right? I already locked the door. So you won't be able to enter my class. So you are going to miss the class, unfortunately. So your input signal just delayed 15 seconds, 15 minutes. However, your output turns out that it's not just another 15 minutes delay. No, it's not just another 15 minutes delay. Okay? So this system It's not time invariant. It's not time invariant. Got it? So actually, in the real world, some of the system is not time invariant. It's not time invariant. Okay? It is time variant. It is time variant. Okay? Got it? All right. So I'm not going to prove it. Just use a very simple figure here to show you that. Okay, let me show you another figure. So this is similar to what I just showed you. So if I have a signal, which is a rectangular box, and go through a time invariant system. Suppose this is the output, suppose, okay? And then if I delay the signal, tau second, delay the signal by tau seconds, then the output also delays also delay tau seconds. But the shape remains the same, remains the same, okay? Now if you look at this one, now suppose this is the input signal and this is the output signal. Now you delay 1 second. The output signal also delay 1 second. Delay another 1 second. This is the output, also delay another 1 second. So on and so forth. However, if you are considering a time invariant system, something is different. This is the input, this is the output. Okay? Now if you delay 1 second, the output also delay 1 second, but the shape is not, they are not the same, right? It changes a little bit. Okay? And again, you delay another 1 second, the shape of the output also changes a little bit. So this type of system is time variant or time variant. Time variant or time variant. Okay? Any question? Okay, another one given by the book. Okay, I think this is very interesting. Considering the modulation, amplitude modulation. Suppose I have a signal. I think everyone brought your laptop, right? Okay, try this. Okay, try open your laptop now, please. Okay, let's run this simple example. All right, so here we can see the very simple amplitude modulation. All right, so once you open your laptop, please run the MATLAB. Okay, follow my command. It's very simple. So let's define a time sequence first. T from 0 to 0.01. Okay, yeah. Up to 10 seconds. Or just, maybe just this. 0.01. 100. Up to 10 seconds. Okay? And then let's define the carrier, M of P carrier. C another one. Another one, you can see WM 1 radian per second. Okay? That's the frequency of the message. And then WC, the frequency of area. Omega C is 10. Okay? Just a very simple example. And the message is sine of WM and E, the area is equal to the sine of WC times E. Okay, so you have constructed the output. This is the, we have output Y of T modulated signal, mod signal, is the messenger, or the message, excuse me, the message times the carrier. So this is a modulated signal. Okay? So now I want you to plot. Okay, create a figure first. This figure 1. And then plot. P, and then mod. Sig. Okay, use the red and dot to plot the signal. And then show the signal. See what happens first. Okay, it will give you 3 minutes to finish this. You should be able to do it very quickly. It's a very simple exercise. First one, I need you to show me your modulated signal. Okay, once it is done, once this is done, okay, let's shift. Now since the message MLT is the input, so this is the system. This is the modulation system. And while this is the output. So once your modulated signal is done, you can plot it, see how it looks. Okay? And then let's shift. So now let's shift. Shift to the message. SH is. That is equal to sine. WM, and times T minus, say, 3. T minus 3, okay? So we shift the signal 3 seconds to the right. Actually, it's a delay. Okay, and once this is done, so put another figure. And then plot. And see what happens. So you can see whether this modulation system is time varying or time invariant, or time invariant. Whether it is time invariant or it is time varying actually. You can? Where is your laptop?
Well, it's hours back.
Not a good excuse. Could you bring the laptop next time? Okay? So anyone can tell me? Can anyone tell me? What do you see? Or what did you see? Whether this amplitude modulation is time varying or time invariant. Are you done? Yeah, good. So if you compare the two figures, okay, especially for the time after 3 seconds. Okay, compare this peak. This one, they are different, right? Okay? And this one was different from this one, right? So I think you can see that actually the outputs are different. You shift your message 3 seconds later, to the right, 3 seconds later. The output turns out to be slightly different, okay? Not so obvious, but we can see that they are different from the original. Okay? So this system is not time invariant, actually it's time varying. Actually it's time varying. Okay, so you can see this one, this peak, and this peak, and this peak, and this peak, they are different. This one, different from this one, this one, and different from this one. Okay? So they are different. So the outputs are different. You can see that there's a slight difference, but that's different, okay? Are you done? Okay. All right, great. So you can see that this one is different from this one. Okay, and here, this is different from here. Okay? Are you done? Amen? But you can see that this is different from this peak. Okay? This is also different from this. Okay? So yes, this is not unvaried, it is unvaried vector. Okay? All right, good. Okay, let's proceed. Any questions? Come on. Are you done? Come on, come on. Are you done? Could you give a hand to your friend? Are you done? Not yet. What are you doing? What happened? You are supposed to install all the tools you need, okay? Oh, huh? Okay. Took too much time to open it. Okay. Okay. So what is the problem now? Yeah. Still have the error message or what? Internet. You don't need internet. You don't need internet. Well, you have to check the license. All right, let me give you another couple of minutes, okay? Help your friend if you are done, okay? Would you give a hand to your friend? Okay, if you are done, then please look at the lecture notes. On page 143, there are some examples for the linear systems. Maybe it's better to read it very quickly because we are running out of time. Okay, please finish it in about 2 minutes, okay? Everyone, would you finish it in 2 minutes, okay? Okay, now in order to speed up a little bit, because we are behind schedule. Okay, so let's use the slide directly, even though I don't like it. Okay, for some of the systems, they can be described by using differential equations. Okay, we will see that later in some other cases. Okay, so look at the coefficients. Suppose the coefficients A0, B1 up to whatever the coefficient, okay? And B0, B1 and up to Bn, okay? Suppose those coefficients are constants, and actually it's easy to prove them. The system is a time invariant system under the condition. If all the initial conditions are zeros, okay? And to the X of t is photo signal. We will see that later. I will show you that. That is 0 for time prior to 0. The system is not initially energized. So let me show you the first one. What is a photo signal? Maybe this is if we consider a causal system, okay, let's consider a causal system for the moment. That means I have an input, I have an output. This output depends on the input in the past, not in the future. Okay, so like this one. These are the output. These are the output. This output depends on the time prior to the time we are considering here. And if you consider this moment, okay, then this output will be affected by the input from here to here. That's it. But look at this one here. If we are considering a non-total system, and we have an input like this one. But look at the output. Before the input is applied, there's an output. Okay, there's an output before the input is applied. What kind of situation can happen? Stock market. Suppose we know that tomorrow there will be a big event. What kind of event? Maybe there will be a war, right? If you know that tomorrow there will be a war, okay, what will happen to the market? Everyone will drop all the cash, okay? And then the stock market will crash right away, even though it is currently today, not tomorrow. The war will happen tomorrow, but not today, right? But today, everyone will drop all the cash, okay, and turn that to gold. So the stock market will crash right away. That's kind of a non-causal system. That's a non-causal system. The output, today's output, depends on tomorrow's event, tomorrow's input. Because you know that tomorrow there will be a war, even though it not happened yet. But people know the message. They will do something. Okay? So that kind of non-causal system. Oh, okay. Give me a few seconds, okay? Let's go back to the non-causal system. So this type of system, okay, we call that linear time invariant system. It is time invariant if initial conditions are 0. If the x of t, the input signal, is auto, means all the signal is 0 for the time prior to 0, because we assume 0 is the initial time for the system. Okay? So nothing happened before the time equals 0, which means the system is not initially energized. Okay? If this is true, if these conditions are satisfied, then this differential equation is time invariant. Actually, it's linear time invariant. Okay? Here we have some simple example. If we consider a differential equation, first order differential equation, this is the first order differential equation. And then we have the solution, I of t, current, I of t. Okay? Now, u is the input unit step function. Okay, the V of t is the voltage source, that's the input. Okay? initial condition. This is the initial value of the current. And then we have some cases, if initial condition is non-zero, for example, I sub 0 is 1. And also we have the input signal. E is 1. Okay, so that's the input signal. Voltage source is the input signal. So we can see that for this condition, this is a complete solution. And it can be divided into two parts. One is for zero state response, and this is zero input response. Zero state response means this is the part for zero initial condition. So only input appear in the solution. And zero input response, this means this is related to the initial condition. No input signal. I'm sorry. This should be for zeros. Okay, let me check it again. This should be for the zero initial condition. And let me double check it again. All right? Okay, and then if initial condition is non-zero, initial condition is non-zero. And also we have a input signal. Then you can see that the linearity will not be set. The linearity will not be satisfied. Okay? So I need you to read this by yourself. Okay? Please read this by yourself. This is very good and simple example, but please read it by yourself. And let me check that. Here I have a little bit problem with this location. Okay? Sorry about this. This is my problem. Okay, so I need you to read this by yourself. Okay? And if you have any question, we can go through that next time. All right, again, before you leave, let me remind you. Next week, there will be no class due to the long vacation. Number 2, please find a term project. Okay? The topic, either you want to use the topic that I show you in the beginning of the class, or you can find your own topic. But if you use your own topic, please let me know, okay, before you dig into the project, okay? And then there will be no midterm exam, the written test. It is replaced by the term project, okay? Okay, so which also means we are going to have a presentation maybe a couple of weeks after the midterm exam, so that you have time to prepare for that. So at first you have to find a proper topic for your term project. Use either my topic or your own topic. Okay, got it? And then finally, the final exam, similarly, there will be no written test for the final exam. That will be replaced by your term project. Okay, so in the end of the semester, you are going to give me a complete report and also an oral presentation. A written report and oral presentation. Okay, got it? Question? Okay, and see you next time after the long break.